Alrighty, so here we are with 12.6. We're talking about segment relationships in circles. And so our objectives are to find the lengths of segments formed by lines that intersect circles and using the lengths of those segments to solve problems. So hopefully we will get there by the end of this. All right, so the first thing here is our chord product theorem. And so this one does technically have a name to it rather than 1161. So either way, chord product theorem means that we're going to take both of the chord pieces and multiply them, which is product. So filling in our pieces here, if two chords intersect, so two chords intersecting in the interior. So again, interior right here, intersecting of a circle, then the products, meaning multiplication, right? Of the lengths. And so now we are going with lengths, notice, and not angles like we've been doing for a while here. So very key that we're doing lengths, and they are equal. So you can take AE, which is this piece, multiplied by EB. So if you know those two lengths, then that is going to equal CE times ED. Okay, so two pieces of each of the chords multiplied. So taking a look at something that would help us with that, notice that we have, as the definition says, two chords intersecting on the interior of a circle. So we're going to take the products of each of the segment pieces and multiply them to be equal. So 14 times x makes up GH. So 14 times x is going to be equal to 7 times 10, which makes up FE. So that means that 14x is going to equal 70. And so if we divide both sides by 14, we're going to get an x of 5. So find the value of x and then the length of each chord. And so since we did find the length of each chord potentially, we know that GH is 14 plus x, which we just said was 5. So GH is 14 plus 5, so 19. And then we also need to find FE. And FE is 7 plus 10, or 17. There you go. So the idea again is multiply the two pieces of the chord. All right, then we've got this next theorem right here. So this is the segment, secant segment. So a secant segment, notice, has a segment, right? But then it also is feeling like a secant because it goes through the circle. So we will reference secant segments in the next definition. And so we want to make sure that we know what they're talking about. So a secant segment is a segment of a secant. Remember, secant line would have gone through both of those pieces with at least one endpoint on the circle. So again, we're imagining this is a secant, but now we have chopped it off so that one of the endpoints is on the circle. So that's point P. And so PM is a secant segment. Turns out NM is also a secant segment because notice it has one of its endpoints on the circle. We also have KM, the one that goes through the circle there, is a secant segment, and then also JM is also a secant segment. So those are all secants potentially because they would continue to go through the circle, but they're segments, so they've been segmented or cut off. So NM and JM are what we call external segments. So these guys out here on the exterior. And so an external secant segment is a secant segment that lies in the exterior of the circle with one endpoint on the circle, which I guess we'll call the circumference because that's actually what it is. But there we go. So secant segments are all of these pieces, okay? But then there's external ones, which are just these two up here. Alrighty. So moving on, we have our theorem that talks about these secant segments. And so if two secants intersect in the exterior of a circle, so that's here at point E, then the product of the lengths of the secant segment and its internal, so AB and BE, so that's the secant segment and then its external, equals the product of the lengths of the other secant segment and external segment. So that means that we are going to take the whole segment AE and multiply it by the outside part. So AE, the whole thing, times BE, just the outside part. And then that's going to equal the other secant segment, CE, multiplied by its outside part, DE. So whole times just the outside part, and then the whole times just the outside part is going to be equal. All right. So taking a look at this again, since we just did this, it's going to be the whole times the outside, and that's going to equal the whole times the outside. But looking at this, the whole piece from G to E is x plus 8, and then the outside part is, I guess there isn't a letter here, so it's just 8. And then that's going to equal the whole on the other one, which is DE, or 9 plus 7. And then times just the outside part, which is just 7. So seeing if we can simplify here, we've got x plus 8 times 8. So we could distribute that in here to get 8x plus 64. Over here on this side, we've got 9 plus 7, which is 16. And 16 times 7 is 112. Again, multiply and then, add because of parentheses and then multiply. And then we can just solve algebraically because it does say find the value of x. So subtract a 64. And we're going to get 8x that equals 48. Divide by 8. And we get an x of 6. So it does want to find the value of x, so we did, and then the length of each secant segment. So we know that GE was supposed to be x plus 8. We now know that x is 6. So 6 plus 8 gives us 14 for GE. And then DE, we already said was 9 plus 7, and 9 plus 7 is 16. So those are the two secant segments, and then x. So I'll circle that as well. Box it. All right. And I didn't make this one orange to match that. That's what I was talking about here. All right. There we go. The next one is tangent segments. So that's going to mean that it's a tangent potentially, but it's been segmented. So a tangent segment is a segment of a tangent with one endpoint on the circle. So notice this is your tangent potentially, and it just has that one endpoint. on the circle. And so in this case, we have A to B and A to C as tangent segments. Again, that's because these points potentially, even though it's drawn a little awkwardly, just touch the circle, and then the rest of the line starts continuing out after that. So, of course, there's going to be a formula with this. And so just as we did before, we're going to have the whole secant segment times the outside part. So in this case, AC times BC. That's what's happening here. And then the tangent segment squared. Because, of course, we needed to multiply something here, so we need to multiply something here, which is just it times itself. So that's our secant tangent product theorem. So instead of just having two secant segments, we now have a secant segment and a tangent. And so to get that value, we have whole times outside and DC squared. So our last example here is to find the value of x. So this is our secant segment. And so remember, we're going to do the whole times the outside. And so the whole piece is ML. And we're going to multiply that by the outside, which is JL. ML is 20, but JL is only 5. And that is going to equal the tangent squared. And the tangent is KL because it just has this one point that it touches. And so now I just take the value of KL, which is apparently x, and square it. So to solve, we need 20 times 5, which is 100. And then we would square root both sides and get a 10 for our x. So value of x is 10, and that's all they wanted. Alrighty. So 3 new ideas here. We've got our secant segments, but then we've also got this chord product theorem. And then we did our secant product theorem. And then our last one of secant tangent product theorem. So lots of multiplying of lengths. So remember that we were talking about lengths and not degrees. So again, we're moving on from degrees. All right, so next is your assignment.